Hello everyone, December 19th. All right. Finally, we have a fresh start on almost all of it. So find if path exists in graph. We have a bidirectional graph with n vertices where each vertex is labeled from 0 to n-1. The edges in the graph are represented as a 2D integer array. Okay. The nodes are bidirectional edge between yes. Every vertex is connected by at most one edge. No vertex has an edge to itself. So there's no cycle. You want to determine if there is a valid path that exists from vertex source to destination. Given edges and integer n, source and destination to true if there is a valid path. Okay, so we just need to find one path. So we build a graph, and what you want to do? You want a DFS or you want a BFS? Maybe DFS is easier. I'm not sure. So you start from something, and then we just, keep going. All right, we keep going and do not visit the one that has been visited before. I guess that's it. You have a visited, and then you just keep going, and then just don't visit the one that visited before. I think I'll go BFS. No, not BFS, DFS. I think DFS will be easier to write. All right, so what do? We have n edges, and then we need to do a graph. Man, I do not like this part very much because it's just what do I call this? Boilerplate. Alright, B, we're gonna do A, okay? And then DFS, we have a node, which is actually integer. And then we have visited, alright, which is a set, and this will return a Boolean value. Then what we say? We say if node is equal to destination, turn true. Otherwise, say for child in graph node, so all the child, and then we say if child is not, hold on, visited.add node. All right, child not in visited, DFS child visited. Right. And then what? Oh, then we have to go say if. When I say if this, and this will return true. So if this is a true and this is a true, if it's a false, then we have to try the next one, and then blah 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 blah. Once we've done everything, we'll return false. Okay, then we run DFS, a source, and a set, and then we return this. All right, let's give this a shot. I didn't use and though. I don't think we need and. Oh, shoot, we need. I see. Man, that's not All right, let's so if node is invisited, turn false. Now we don't check it here. We just DFS. Okay. Yeah, let's put this one first. Okay. And then, oh my god, we have to go. Wait, hold on. Why? I was seeing this is unconnected. So from 0 to 5, I just we just can't go. Nah. I don't think so. I think the n is not necessary. No, I think n is not necessary. I think this should be sufficient. Let's try this. Yeah, I think it's sufficient. I don't think we need n. We just, because all we want to do is find one path, and then that should do. Yeah, nothing too special. Should I put it that way? All right, 1971 DFS. Okay, I want to take a look. BFS and DFS. Yep. They use this, which is fine. It's the same idea. Okay, let's try this. Delete greatest value in each row. We are given n by n. Perform the following operation until grid becomes empty. Delete the elements with the greatest value from each row. If multiple such elements exist, delete any of them. Add the maximum of deleted elements to the answer. Let the number of columns decrease by 1. Return the answer after performing. Hold on. So just every single time we want to delete the largest value. So it'll be 4 plus 2 plus 1. That's what you want to do? The maximum delete to the answer. 4 plus 3 plus delete the element with the greatest value from each row. Okay, at the maximum of the deleted items. Okay, it's 4, 3, 1. I gotcha. Okay, so we can sort them. All right, we can sort them, and then we need to sort them again. No, we don't need to sort them again. We sort them, and then we just simply find the maximum. I mean, it's very small test case, so basically, however we want, we can do it. It doesn't really matter too much. I mean, we can even like brute force this. I think it's fine, but we won't do that. So what we're gonna do is we'll sort each row. Okay, sort each row and go from right to left, and then every time we just collect the whole column and then do whatever we need to do. We need to say for row in grid, row.sort reverse equals true. Okay, And then we're gonna say rest is gonna be 0. And then we say for row in grid. Okay. And then for I, that's not I. For J, that's not J. We don't do for row in grid. No. It should be for J in range, len grid 0. Right, len grid 0. Minus 1, minus 1, minus 1. Okay, so that's the first column. So what we need to do is res plus equal to the maximum of for I in range len grid. Okay. Grid I and J. Right, we just go through every one, we get a maximum, and we'll return the rest. Okay, let's try this. This shall be 8. And I think the next one is 10. That shall be 10. So we have a grid. Let's delete grid. Okay, looks to be promising. Okay, let's go. Right, so that's done. So what's the runtime? Oh well. Is that the same? Oh, mn is not necessarily the same. So we have O M, then we have n log n, that's this part, plus O n, n, right, this is n, this is m, O m n. So that's kind of how it looks like. Okay, so that's that. Next one. Longest square streak in an array. Given an integer array, a subsequence is called a square streak. That's subsequence. If the length of the subsequence is at least 2, and after sorting the subsequence, each element except the first element is the square of the previous number. Ooh, each element is the square of the previous number. After sorting, return the length of the longest square streak, or minus 1 if there's no existing. Okay, because we can sort them, so it doesn't really matter where they occur, right? So for this case, all we need is to find. So we have 4, we say, is there 16? Yes, we have 16. Is we have 32? No, 32. 16 squared is not 32, man. And because we can square, I think we can sort them first. So it doesn't really matter, because like no matter what subsequence you have, they say you can square it. So you can always change the order. So we can change the order first. So if we change this order, what do we get? We have 2, 3, 4, 8, and 6, 8 and 16. So we look at a 2, we say, okay, do we have a 4? Yes, we do. Do we have a 16? Yes, we do. So that will be 3. And then we'll look at the second one. Do we have a 3? Do we have a 9? We don't have, so that's it. 4 we already checked. 6, 8. So that answer is 3. So yeah, we're gonna sort it first, and I didn't say they're all unique, so actually it doesn't really matter, right? It does not really matter, unique or not, because each one can only serve, if they want to be part of the streak, they only need to have to serve in one. They can only do in one streak. So we can just set them, right? We do set them, and we just go from the front, the first one. And then we simply, we can remove it, or, nah, we don't have to remove it. We just turn it off, all right? And then we just double it, we see if it's there, and double it, see if it's there. Ooh, see if it's there. Oh yeah, we can just remove it, right? We double it, and then we just remove it from the set. And then every time we hit a new value, we have to check if the new value is inside. If it's not inside, then we don't do anything. Let's try this. I think this direct solution shall work. Why? Because each time we hit every value once. Yeah, exactly. We hit each value once. And as we expand, because we're doubling, so it's very fast. We'll exhaust the entire thing. So it's O(n) log n. That's how I think this one is. But let's try. So first things first, I'm gonna sort this, and then let's use scene. Okay, nums, and then for n in nums, right? We say if n in scene, not in scene. Okay. Oh, hold on. We say res equals 0. Okay. You should do -1. It's fine. And then we say count. Count is going to be 0. And then we say while. We're gonna do start. We say s gonna be equal to n. So while s is not in nums, right? So s is not in nums, not in scene. No, if s, it's not seen. Come on, this is unvisited, unseen. Then it's if s is inside unseen, then we say count plus equal 1. Unseen dot remove s, and s times equal to s. Basically just double it. And then we try it again, and then we do again, and we try it again, we do again until we get out. And we say if count is larger or equal to 2, then res equals maximum res and count. Right? Then we go for the next one. And then we do blah blah blah, and at the end we'll return res. Let's see if this one works. Oh, I can set up some test case for this. That's actually good. But there'll be a lot of -1 if I set up a test case, I guess. So nums longest. Okay. Nah, I think this should be right. I don't see any issue with this. Just go for it. Oh, it's taking a while. Yeah, it's not the fastest, but we did pass. Oh, I got another, I win another Kindle book. That's good. I have so many books. It's good to read, right? Sort nums and check each value, right? Check each value. Since we we square, right, on each value, it will be fast to exhaust. Exhaust all possible, right? All possibilities in nums. So I call this O(n) log n, right? So this is O(n) log n. This is O(n). This is O(n). This part, because we double every time we double, right? So to exhaust every possibility, that will be log n. So we call it O(n) log n. But it's kind of slow, so we can take a look, see. What does it say? Extract through to death. Ha! This is a DP. Oh, is it faster? Yeah, it's still O(n) log n. I don't see it's faster. Okay, so what do? We sort it. Oh, you find the root. And then, which means we're saying is ending in a certain thing, how long it is. I think that's what they're trying to do. All right, so if I know, I want to know ending at my current value, how much it is. So I go to the front, go to its square root, right? We'll go to square root and then we just plus 1. If not, yep, which means, I mean, this is not DP, this is just, so we could, okay, so, yeah, I know what they're trying to do. Can we go from front to back? No, front to back. Well, it will be going front to back, but every time, man, I just don't want to do this computation, man. If I sorted it, and I go from the last, can I go from the last to front? So I don't have to do SQRT. That's basically what I don't want to do. I don't want to do SQRT. So if I don't want to do SQRT, oh, if you don't want to do SQRT, how do you know? So I say if this is 1, right, and I would find something and I have to double it. And if I double it, then how do you find it? How do you find it? Man, are you telling me you also use a mapping to get the oh no, we don't care about. Oh, okay, I see. We don't care about. Okay, yeah, that's fine. So we go from right to left, and every time we find this one, and we say if double's in it, then we do it. If double's not in it, then we don't do it. Right? That shall work. That shall work. So we are going to, let's see, we can do it this way. So we have to sort no matter what. Yeah, actually you don't have to sort in this case. Now you do have to sort. Wait, do you have to sort? Yes, you have to sort. Yeah, we have to sort. And then we are going to get a counter. Okay, we can do a counter. Okay, we can do a counter. What do? We say counter equals counter. And then we basically say for I range len nums -1, -1. Okay, because we're going right to left. We say if nums I times nums I is in counter, which means it's the square is in counter, then let's call it counter. Nah, let's call it DP. Yeah, counter sounds weird. No. DP nums I shall equal to DP nums I times nums I. Do you have to do it twice? Nah, we say square equals to this. Let's just compute it once. Okay. So if square is in it, then this shall be dp this square plus 1, else then dp, oh, we can do this way. I have an even better idea. Say this equals 1 plus dp dot get sq 0. How about this? We can actually just, because it's a counter, so we can actually just do this. which is totally fine. Which means I only need to do this, which is fine. Right? Yeah, if it doesn't exist, then it will be just 1. If it exists, it will just +1. And at the end, we just return dp. Oh, we need the maximum. Rest equals -1. Right? And then we say if dp nums I is larger equal to 2, rest equals maximum rest dp nums I, and then we'll return result. That, oopsie doozy, what the hell happened? Collections. Okay, so this, yeah, this is actually better. This is a DP solution. Might be faster. Okay. It's easier. That's for sure. I mean, we can even not do this. Right? We can even not do this. We can say rest equals maximum dp dot values. Right? And then we return rest if rest is larger equal to 2, else -1, something like this. And we don't have to do the extra check. Okay. Let's see. This one work? It's the same. All right, so that's that. Next one, design memory oh, holy crap, memory allocator. You're given, hold on, I think I forgot to like the question. I think it's a good question, I like it. You're given integer n representing the size of a 0-indexed memory array. All memory units are initially free. You have a memory allocator with the following functionality. Allocate a block of size consecutive, free, and assign it ID. Okay, so we probably need to say a range. The ID will be pointing to a range. And the free will free all memory units with a given, interesting idea. Multiple blocks can be allocated to the same ID. Of course, multiple blocks, because you said allocate a block of size, right? They're just the consecutive blocks. They all become the same ID. You should free all the memory units with MID, even if they were allocated in different blocks. Hold on, what does it mean? You should free all the memory units with this ID, even if they were allocated in different blocks. Huh? What does that mean? When we allocate, we do allocate and assign it the, we provide the ID. Oh, so I can allocate, let's say I call allocate 2 times, okay? And will be two non-consecutive block of memories associated with the same ID. And this is saying that that's why I say multiple blocks can be and should free all the memory with this, even if they are allocated in different blocks. I see what it's talking about. Okay. Implement this. We allocate what initiates this and a memory of size n. Allocate or find the leftmost block of size, continuous, consecutive free memory units, and allocate it with the ID this. Return the block's first index, which is true. First index and size, we get the whole thing. If such a block does not exist, which means, well, the only thing that does not exist is we don't have enough memory, then we'll return -1. If we do, we do it. And when we call it, because when we call allocate, free, allocate again, you see it will be the same. Free will free the memory. Okay, this is a very good question. I'm very intrigued. Let's see how we can do this. So we have an array. Okay, we have the size, and then when we allocate, because it has to be left first, so the first allocate we can get, so it definitely has to be the MID, and we need to have a mapping. MID will map to, let's say, the start position and end position. Okay, we have a start and end position, all inclusive. And then the next one comes in, then we need to keep track. Ooh, keep track. That's... Ooh. So difficult part. Yeah, if we just keep allocating, that's fine, because everything is leftmost. So we always have an end position, and we just keep adding to it. And we can use the mapping to associate MID with a range. Now the problem is when we can free a block. We can free an ID that's associated with wherever the block is, and then then our memory has an open space. Right, we have an open space in between. So now we have an open space in between, and next time when I want to allocate, I need to see if I can fit things inside this open space. Dude, how am I supposed to do that? Open space. Huh. Ooh, this one is not simple. Yeah, so ID is easy. Free is also easy. Free, all we need to do is, we just remove it from the mapping that's freed, all right? But when we remove, we have to know which part are removed. Ooh, there gotta be an easier way to handle this. So, and especially when you remove, for each range you remove, you probably have to check on the range nearby and to see no, remove is fine, but it's when you remove, if we remove, I'd say 2 blocks of memory that's consecutive, and then the empty space need to be joined, right? Holy crap, how am I gonna do this? We can have 2 mappings. So one mapping is, let's say, MID to range, and the other mapping could be range to MID, right? Why do you want range to MID? I don't really want range to MID. What I want is the range itself. That doesn't make any sense. So when you okay, I need like available space. All right, I need available space, like from where to where is available is available space. Okay, from where to where is available space. If I had solved that, then allocate is the same. I just go through all the available space and try to see if the size can fit in. But hold on, allocate. The leftmost block of size, consecutive, free. The leftmost block of free memory. So if it doesn't fit, it just doesn't fit. right? Let's go through the example. We have to make sure that we are talking about the same. And look, we have 1,000. The size not too big. Okay. Anyway, location. Allocate. We have 10. Allocate 1. So the leftmost we do a 1 with ID is 1, and then ID is 2, ID is 3. Good. And we will free all memory units with ID 2. And I have 1. So now 1 unit with ID 2. Okay. And then we allocate 3 position with 4. Okay. Allocate 1 position with 1. That's correct. Allocate 1. And then free 1. So we free these. Nice. Oh, 3 units. 10. We don't have 10. Free 7. We don't have 7. Damn. So yeah, you're basically just saying you have to find all the empty spaces, right? And you can go through all the empty space, and the first one from left to right, the first one that fits, then you will put it in, right? And then you'll update. Okay, so that's fine. Now that's a sign, and then the free, right? We need to also keep track on the free. Okay, so we can, we say this is the free, and then because I use it, I'll change it. How do I keep those? How do I keep those in check? Keep those sorted. I guess you can't. I don't know. I guess you just... Oh man. Let me think. Yeah, we can remove. And we can insert. It can be like bisect insert. So we'll keep everything in order. I think we can do that. Right? Yeah, I think we can. In fact, we don't have to. Yeah, we'll have to remove it, but we don't have to. Because, yeah, I see what you're trying to say. No, we have to insert. Remove. Yeah. Okay, so that's allocate. How about remove? So from the MID, I know which ranges need to be removed. Okay, so remove just means we have these range will become free. All right, these range will become free. So what do? We have original free, or those are already free positions. Now I have a new one, so basically this one is going to be free. So we need to go one by one and see if we can join. right? So we have, say, the start. Oh my god. Compare the start to the... Oh my god. Compare the start to start. No. We compare the start to end. Right? And if it's larger, then we move on to the... How do we do this? Hold on, 1,000, right? 1,000. Maybe what we can do, we can go through 1,000. Okay. Hold on. What you saying? We have an array with 1,000 positions, and then we put, I don't know, doesn't matter. We can put a 0 as a start, 1 as end. Okay. So, when we say remove, yeah, so these are all open, right? So in the beginning, we have this, and then do something, become this to this. Yeah, so we start is, let's say 0 to 1, so these are all good. And then we're gonna allocate. I don't like that. Right, say 0 to 9, that's the empty space. Then we allocate 1, 1, and then we say, oh, we have a 9 plus, we have 10 position, 10 lengths, and the first one requires 1. So we say, okay, we'll do it. And then we say ID is 1, we'll have 1, 1. No. So 1, 1, we have start from 0, right? And then we take 1. So we say 0 to 1 is gone. So it'll be 0 to 1. No, 0 to 0. Right? 0 to 0. And the empty will be from 1 to 9. And the next one we do another one, but the ID is 2. So 1 to 9 is good. So we go from 2 to 9. And then we have 1. Starting from 1, ending at, so that's just 0, 0, 1, 1, right? Next is 3, and then we're just going to keep going. So we're going to do 2, 2. Okay. 2, 2. Next we're going to remove 2. So we're going to remove 1, 1, right? When you remove 1, 1, which means from 1 to 1 is going to be empty space. So we will add 1 to 1 into this empty array. We have binary search and then insert it. So now this empty array is going to be, oh, hold on. So this is 3, 9. And then we find where I need to insert. And then we compare to the front and back. That's the one. And then we say, okay, it's the front. Then we add 1, 1. Right, so we use the left to know where I need to put, because they will not overlap. That's the thing, they will not overlap. And then we just check on the end, right? If they're the same, then we don't have to insert. If they're not the same, so we insert. So now we have 1, 1, and 3, 9. I have to remove 2. Now we put 3, 4. We need 3 positions. The first one doesn't have 3. The second one we have 3. So that will be position 3. Not position 3. No, that's 4. ID is 4. So ID is 4. So from 3 to 9, we need 3. So 3 plus 3 is 6. So the empty will be 6 to 9. So the thing will be 3 to 5, right? 3 to 5 will be 4. And then 1, 1. So we go, oh, 1, 1. We have it. We have it because we have 1, 1. That's the position. And then from 1, length is 1, so that's good. 1 plus 1 is going to be 2. 2, that's the thing. We have 1 to 1 is empty. And 1 plus 1 is 2. So, oh, hold on. So 1, 1, we can put 1, 1 in here. That's fine. And then this one, after this, is going to be, because that's only 1. Right, so this one just gone. Right, well, you can delete this one. Doesn't exist anymore. Yeah, I think we can just analyze it. And then when we have 0, 0 and a 1, 1, we can see if the front and end is, it's different by 1. Oh, when you add, it's the same thing. We have to know. Oh, but it's the same logic. It's the same logic. All right, we can do this, but the question is, do you want to do it today? Honestly, I don't, but I kind of know how I want to do it, so I'll leave this for tomorrow. All right, I'll see you guys